Hello dear students, I am Rana Kumar, your physics faculty at Akash, and a very warm welcome into this session in which we are going to discuss the paper mock test 3, AITS plus mock test 3 that was conducted on 2nd of February 2025, right? Now let's move towards the first problem, let's head towards the chapters. Let's head towards the chapter that we are going to discuss in this session. It will be system of particle and rotational motion. It will be moving charges and magnetism, electromagnetic induction, dual nature of radiation and matter, and thermal properties of matter, right? Now, let's move towards our first problem for this session. It says that photons, and it is a problem based on the chapter of dual nature of radiation and matter. It says that photons with energy 5 electron volt are incident on a cathode C in a photoelectric cell. The maximum energy of emitted photoelectrons is 2 electron volt. Now, when photons of energy 6 electron volt are incident on C, no photoelectrons will reach the anode A if the potential of A relative to C is. So, you need to understand some basic diagrams to, to understand the problem. See, I'll try to draw the basic setup for you to understand how to solve such kind of problem. So there you have, there are two plates right over here, right? Let me call this as your, emitter plate, and let me call this as your collector plate, right? And the light rays will be incident upon this, and photoelectrons will be ejected from the emitter plate, and they will move towards the collector plate. So the potential between them should be, if I talk about potential between them should be like this, and obviously this potential can be varied, but potential setup is like this. So this one is a negative potential, this one is at a higher potential as compared to the emitter plate, right? So this is your cathode, and this one is your anode, right? Now, the light is incident upon the emitter plate, and electrons, they move towards the collector plate, right? So if this is at a higher potential, and if this is at a lower potential, so whatever photoelectrons will be ejected, so you can see that the direction of field will be in this direction. So the force experienced by the electron will be in this direction. So the electrons will move towards the collector plate because it is at a higher potential with respect to the emitter plate, right? Now the problem says that photons with energy 5 electron volt are incident on a cathode C. So what happens is that, okay, so photons with energy 5 electron volt energy photons are incident upon the collector plate, and the maximum energy of emitted photoelectrons is 2 electron volt. So you remember this equation, that Kmax, maximum kinetic energy of emitted photoelectrons, it is equal to incident energy minus the work function W naught, right? Kmax, it is equal to E incident minus W naught. Now incident energy for your case is 5 electron volt, and the maximum kinetic energy of emitted photoelectron is 2 electron volt. So it is 2 electron volt, and this is minus W naught, right? So work function from here, it is coming out to be equal to 3 electron volt. This was the first part of the problem. It says that W naught, it is equal to 3 electron volt. Now, in the second part of problem, they say that when photons of energy 6 electron volt are incident on C, no photoelectrons will reach the anode A if potential of A relative to C is. So I'll draw the setup over here. So this is your cathode, and this is your anode, right? and the light rays are incident upon it, and photoelectrons are ejected from this plate C. Now the condition is that no photoelectron should reach the anode A. So no photoelectron will reach the anode A. It means that you have to stop the electron with the maximum kinetic energy, that is Kmax. If you have stopped the electron which is having the maximum kinetic energy, then other electrons will eventually be stopped, because since the maximum one is stopped. Now how to stop? See, if you try to maintain the anode at a negative potential with respect to cathode, right? Let me say that I am doing what? I am maintaining this anode at a negative potential with respect to cathode. So what happens is that even if the electron is ejected from the cathode, due to the negative potential of anode, they will be repelled. They will not move towards cathode, they will not move towards anode, they will be repelled. So all I have to do is to maintain it at a negative potential with respect to the cathode. And since I have to stop all the electrons, so I have to maintain a potential such that the maximum kinetic energy electron is also stopped, right? Now you see that when photons of energy 6 electron volts, so Kmax, we know the equation, it is equal to E incident minus the work function. So incident energy in this case is 6, right? Minus work function we just calculated is 3. So 3 electron volt is the maximum kinetic energy of the electron, and you need to stop this one. So if the potential of cathode is V, then it should be at a lower potential, and since you need to stop the photoelectron with maximum kinetic energy of 3 electron volt, it should have V minus 3. The potential of this should be V minus 3. So relative to cathode, the potential is V minus 3 minus V, that is minus 3 volt. So minus 3 volt, if you maintain the potential of the anode, the maximum kinetic energy will be stopped, right? The maximum kinetic energy photoelectron will be stopped, right? So minus 3 volt is the correct answer to this problem. That means option 4 should be the correct answer to this problem, right? And yes, I hope you understood this concept. And if you understood this concept, let's move towards the additional problem that I have kept. If you understood the previous problem, you should be comfortable in doing this. It says that in photoelectric experiment, the collector is at 2 volt with respect to the emitter plate made up of copper, and the work function is given to you as 4.5 electron volt. The emitter is illuminated by a source of monochromatic light of wavelength 200 nanometer. The maximum kinetic energy of the photoelectrons reaching the collector will be. So you need to calculate the maximum kinetic energy of the photoelectrons reaching the collector. Now see, I'll draw the setup again. This is your collector plate, this is your emitter plate, right? And the collector plate is at 2 volt with respect to the emitter plate. So if this is at V, so this is at V plus 2, right? Now, work function is 4.5 electron volt. The emitter is illuminated by a source of monochromatic light of wavelength 200 nanometer. So light comes over here, and the wavelength given to you is 200 nanometer. Now you first you need to calculate the energy associated. So it will be equal to E. It is a standard calculation. E is equal to SC by lambda, and you should know the standard value of SC, right? And you should know the standard value of SC. It is 12,400 electron volt angstrom, right? So I'll convert the wavelength also in angstrom. So wavelength is given to me as 200, so it will be 2000. So let me cancel this. So it is coming out to be equal to 62 by 10, or 6.2 electron volt. 6.2 electron volt. Energy is incident. 6.2 is the incident energy, and you first need to calculate the maximum kinetic energy. So Kmax will be equal to the incident energy minus the work function, that is 4.5. So 6.2 minus 4.5. You subtract this, it will be equal to 1.7 electron volt. Right, if I try to subtract this, so it will be equal to 1.7 electron volt. Now what do we need to calculate? We need to calculate the maximum kinetic energy of the photoelectrons. So it should not be 1.7 electron volt. Why? Because since as the electrons will be removed from here, the Kmax electron, it will be it will move towards the anode because it is at a higher potential, and the potential differences between the collector plate and emitter plate is 2 volt. So this much energy will be added into this, so it will be equal to 1.7 electron volt plus 2 electron volt, that is equal to 3.7 electron volt. So this should be the maximum kinetic energy which is reaching the collector, right? I hope you understood this. Now let's move forward to the second problem of this paper, and it was problem 26 of the original paper. It says that the de Broglie's wavelength associated with a particle of mass 2 kg moving with a velocity of 100 meter per second is. So you need to calculate this time the de Broglie wavelength. So the relation is lambda, it is equal to h over p, right? This is the relation that you know. Lambda, it is equal to h over p, and you should know that this relation, it tells you that a particle can have the a body or a particle can have the particle nature as well as the wave nature. So the momentum part, it is coming from the particle nature, and the wavelength part, it is coming from the wave nature. And this equation, this beautiful equation, tells you how to relate the particle nature as well as the wave nature, right? So if a body is having a very large momentum, in that case, if a body is having a very large linear momentum, to be precise, so its wavelength will be very less. So obviously you will see the particle nature will dominate over the wave nature, right? And if the momentum of the body is very less, in that case the wavelength will be more, so wave nature will dominate over the particle nature, right? So this is the beautiful equation to determine the de Broglie wavelength of a particle which is having a linear momentum p. So this one is your linear momentum, right? And this is your de Broglie wavelength. De Broglie wavelength. Right? Now let's head to the problem. It says that the de Broglie wavelength associated with a particle of mass m equal to 2 kg and moving with a velocity 100 meter per second is. So first you find out the linear momentum p. It should be equal to product of mass into the velocity m into v. So what is the mass? Mass is 2 multiplied by the velocity, that is 100. So it is equal to 200, right? And de Broglie wavelength you need to find, it will be equal to h over p. What is the value of Planck's constant? Can anyone tell me what is the value of Planck's constant in the comment box? Till then I'll write it over here. It is equal to 6.634 into 10 raised to the power minus 34, right? Upon p, that is equal to 200, right? Simple calculation, it should be equal to 6.634 by 2 into 10 raised to the power minus 36. So if I try to solve this, it will be equal to, if I try to solve, I will solve this over here, it should be equal to 3.3 into 10 raised to the power minus 36, and that too in meters. So this is your answer to this problem, 3.3 into 10 raised to the power minus 36 meter, which means that the correct answer to this should be option 2. So this one is wrong, this one is also wrong, and this one is also wrong, right? Okay, yes, second option is the correct answer to this problem. This was a simple problem, easy calculation. You just need to remember the value of Planck's constant. You just need to take care of the units and you are good to go with such kind of problems. Now, if you understood what is the concept of de Broglie wavelength, how do we relate the wave nature and the particle nature, right? So attempt this problem and I'll show you the problem. This problem was asked in the actual NEET examination and the problem is right in front of you. There you go. This problem was asked in NEET 2022 and it says that the graph which shows the variation of de Broglie wavelength. So graph which shows the variation of de Broglie wavelength lambda of a particle and its associated momentum p. So you need to pick the graph which shows the variation of de Broglie wavelength of a particle and its associated momentum p. So the relation, we just know that it is equal to lambda, it is equal to h over p, right? This is the relation. Okay. So dear students, what about this relation? It says that if the momentum is very large, mathematically it is written as P tends to infinity. What is the meaning of P tends to infinity? It means that the momentum is very, very large. In that case, the de Broglie wavelength, it should tend to 0. Obviously, if the linear momentum of a body is very high, then the particle nature is going to dominate over the wave nature. So de Broglie wavelength will tend to 0. And the reverse scenario is also possible, that if the linear momentum is very small, how do we write it mathematically? It means that the linear momentum is tending to 0. In that case, the de Broglie wavelength will be very high, and we write it as infinity. That de Broglie wavelength is tending to infinity. So that is how you write it mathematically. Now, see that if I try to draw the graph, it says that I'll plot P over here and I'll plot lambda over here. Now, the explanation says that the graph should be something like this, right? It means that when P is tending to infinity, you can see that the de Broglie wavelength is tending to 0. Here is your 0, right? That is what we concluded from the equation also. And other part, that if this P tends to 0, you can see that if the linear momentum is tending to 0, then de Broglie wavelength is tending to infinity, right? So de Broglie wavelength is tending to infinity. So this should be the correct variation, right? And the correct answer should be option 3, right? And it was very simple also. This variation, it is also called rectangular hyperbola, right? So the variation for rectangular hyperbola is a standard one, right? So if y is equal to c over x, or y into x is equal to constant, the graph would be something like this, right? So this one is your y and this one is your x. Either you can remember it by the graph, or you can just go through the concept. Either way, you can get the answer to this problem, and this was the actual problem of the NEET examinations, right? Now, dear students, let's move forward to the next problem. And it says that, okay, a problem based on the chapter of moving charges and magnetism. It says that a thin, long, straight wire. Okay, you have a thin, long, straight wire carrying a current I. The variation of magnetic field B produced by this wire with respect to perpendicular distance r from it is correctly represented by which of the following graphs? So you have a wire something like this. It is carrying a current I, and you need to show the variation of magnetic field. You need to show the variation of magnetic field with distance r from this wire. So for this, I can use the Ampere-Circuital law, which says that closed integral of B dot dl, it should be equal to mu naught into I enclosed, right? And please comment what should be the shape of the magnetic field of this current carrying wire will be concentric circles. So it should be something like this, right? So let me take an Amperian loop like this also. This is my Amperian loop, and it lies at a distance of r. It lies at a distance of r from the current carrying wire, right? Now, if I try to solve this integral B dot dl, you are very well aware that this B dot dl, it will be equal to, so angle between B and dl, it will be 0, obviously. So B into dl, it should be equal to mu naught into I enclosed. I have opened the dot product, angle is 0, cos 0 is 1. Since this B is constant, over this Amperian loop, this B is constant, I'll take this out. So it becomes B into close integral dl. It should be equal to mu naught into I enclosed. Now what is the I enclosed? It has enclosed the current I, so mu naught into I, right? And what should be the integral of dl? B, the integral of dl, it should be equal to 2 pi r. It should be equal to mu naught into I, right? So B should be equal to mu naught into I over 2 pi r. This is the expression right in front of you. B that is equal to mu naught I over 2 pi r, and you need to check the variation. So I'll write the equation right over here. B it is equal to mu naught into I over 2 pi r. Now if the wire is same, the current is held constant, then you can see that if r is very large, that means if r is tending to infinity, in that case B should be very small, that means B should be tending to 0. And the reverse case is that if r is very small, in that case B should be tending to infinity. Just like the variation of de Broglie wavelength that we just discussed before this. So what is the graph representing this variation? Can anyone tell me the answer? Can anyone tell me the answer to this problem? So it is a second option. Second is the correct answer to this problem. Option 1 is wrong, option 3 is wrong, and option 4 is obviously wrong. It again, the variation is rectangular hyperbola. You can see from this that if r is very large, B will be 0, and if r is very small, B will be tending to infinity. Okay, Danish is saying that, sir, I find this topic very difficult. Okay, I'm trying to ease out this topic for you. Now, dear students, if you understood this problem, have a look at this problem. And again, it is an actual problem of the NEET examination. It says that, there you go, it says that, and this problem was asked in NEET 2022. It says that a thick, and if anyone knows how to solve this problem, please put the answer in the comment box. Up till then, I'll go through the problem. It says that a thick current carrying cable of radius r carries current I uniformly distributed across its cross section. The variation of magnetic field B due to the cable with the distance r from the axis of cable is represented by, and it is not a normal question, it is the actual NEET examination problem. So you must attempt while going through the live class, and if anyone knows the answer, you can just put the answer in the comment box. So it is a slightly difficult problem as compared to the previous one, right? So what is happening is that this time we have a thick wire. I am drawing the cross section of the wire. So this is the center of the wire, and the current is distributed across this whole cross section. And let me assume that the radius of the wire is r. Radius of the wire is r, right? So, okay, someone has commented the answer. So for the first case, I'll take the condition when my distance is less than the radius, r is less than r. So I'll take my Amperian loop, something like this. Right, this is my Amperian loop. I'll perform the close integration B dot dl. Again, it will be equal to B dl cos 0, right? And since B is constant, it will come out of the integration. So B and integral dl, it becomes 2 pi r. This was the simple part. And it should be equal to mu naught into I enclosed. Now the problem is how to find the I enclosed, because in the previous case whole of the current was enclosed. It was a simple case, but in this case the current is distributed across the cross section. Okay, someone is commenting the answer, someone is commenting 2, someone is commenting 3. Let us first try to find how to find the I enclosed. See, if this wire is carrying current I, it is distributed across the area pi r square, right? And if this loop is carrying current I, so it should be distributed across the area small pi. The radius of this Amperian loop is small r. So it should be distributed across pi r square. So I can write that I over pi r square, not I over capital pi r square, it should be equal to small I over pi r square. So the small I, the current enclosed, this is the current enclosed, it is equal to I over r square into small r square. Right, I hope you understood how to find the current enclosed. Now you just need to write the formula. So it should be equal to B into dl is 2 pi r, and it should be equal to mu naught into I enclosed. So I enclosed is I over r square into small r square. If I simplify the expression, it will be equal to mu naught I r over 2 pi r square. Okay, so the graph for r less than r, so it is b, and if this is r, so till the radius the graph should be something like this, and it is r equal to r. For this part, b is directly proportional to the distance from the center of the wire. B is proportional to r. Now let's move to the second part. If I draw the Amperian loop, which is which is at a much which lies at a distance it is also small r, but this time it is I'm taking the case, I'll write it over here, I'll write it, okay, this time I'm taking the case when r is greater than r, right? So for this case I can write that again, close integral of b dot dl I have to perform. So by the similar logic it will be equal to b into 2 pi r, right? So if this is your cross section, this is the radius of the wire, so I'm taking my Amperian loop something like this, it is small r, so it becomes b into 2 pi r, and it is equal to mu naught into I enclosed. Now the whole cross section lies within the Amperian loop, so it should be equal to mu naught into I. So b is equal to mu naught I over 2 pi r. B is equal to mu naught I over 2 pi r. So for this case, b is inversely to 1 over r, right? So for this case, b is inversely proportional to 1 over r, so variation should be something like this. Over here, b is inversely proportional to 1 over r, right? So I hope you understood this, and if you understood this, then the correct answer to this problem, it should be option 3. For this part, b is proportional to r, and for this part, b is proportional to 1 over r, right? Okay, dear students, I hope you understood this problem also. Now let's move forward to the next problem, and this problem is based on the chapter of thermal properties of matter. In this problem, you need to find the equivalent thermal conductivity, right? Let me go through the problem first. It says that two rods P and Q of different material are welded together as shown in the figure. Their thermal conductivities are 2K and 3K. Now the thermal conductivities are 2K and 3K. The thermal conductivity of composite rod will be, and both rods have equal cross-sectional area. So you need to find the, the thermal conductivity of the composite rod. So if I try to draw the composite rod, it should be something like this. This is my composite rod. The length over here is 2L, and the area is A. Area over here is also A, and let me assume that the equivalent thermal conductivity is K equivalent, right? Right. So I can write that R, the equivalent thermal resistance, it should be equal to R1 plus R2. Now anyone can tell me the formula for the thermal resistance in the comment box. If you know, if you know, you can tell me what is the formula for the thermal resistance. Up till then I'll try to solve. So R, thermal resistance, it is equal to L over Ka, right? So R equivalent, first learn how to write the R equivalent. So this is your composite rod. For this, if I want to write R equivalent, it should be equal to 2L over K equivalent into A, right? Okay, someone is commenting me the answer. How to write the thermal resistance for this? It will be equal to R1, it is equal to L over Ka. And how to write the, for this, it is equal to R2, it is also equal to L over, not Ka, it is equal to 2Ka. And for this, it is equal to L over 3Ka, right? So you just need to use the concept that R equivalent, it is equal to R1 plus R2, right? So R equivalent, it is equal to 2L over K equivalent into A, it should be equal to R1 is L upon 2 KA and R2 is L upon 3 KA. Now let's cancel out the common terms. Yes, LA and LA. I'm cancelling it out. So if I try to do the calculation, it is equal to 2 over K equivalent. It is equal to, I'm taking as 1 by K as common. So it is 1 by 2 plus 1 by 3, 1 by 2 plus 1 by 3. So it is equal to 2 over K equivalent. It is equal to 1 by K, I am taking as common. It is equal to 5 by 6. So K equivalent from here, it is equal to 12K by 5. 12K by 5. So K equivalent, that is what we need to find. It should be equal to 2.4K. I hope you understood. Yes, someone is commenting the answer. Yes, you can remember the formula. Otherwise, you can use this method also. So K equivalent is coming out to be equal to 2.4K. That means option 2 should be the correct answer to this problem. Now, if you understood this, just tell me what should be the equivalent thermal conductivity of the composite rod if the rods are connected like this. So this is 2K, this is 3K, the length is L, and the area is A. What should be the thermal conductivity, equivalent thermal conductivity for the composite rod that is shown to you? If you know, just put the answer in the comment box. And you very well know that this is a parallel combination. For this combination, you should write that 1 over R equivalent, it is equal to 1 over R1 plus 1 over R2. Right, so 1 over R equivalent, it is equal to 1 over R1 plus 1 over R2. What should be the look for the composite rod? It should be something like this. So the length is L, this area, it becomes 2A, and equivalent thermal conductivity is K equivalent. So if R is L over Ka, then 1 over R, it should be equal to Ka by L. Right? So if I try to solve this for you, anyone getting the answer? Okay, someone is commenting the answer. Let me solve this for you. So I'll write K equivalent into 2A by L. It should be equal to 2K into A by L plus 3K into A by L. So A by L, A by L, A by L cancel. So K equivalent for this rod, K equivalent is coming out to be equal to 2K plus 3K is 5K by 2. That is 2.5K should be the equivalent thermal conductivity for the rod when they are connected in a parallel combination. I hope, okay, yes. 2.5K, 2500. Okay, so 2.5K is the correct answer, you know. So you now you are confident and you are clear how to deal with the equivalent thermal conductivity when the rods, they are in, you know, parallel combination, or when the rods, they are in series combination. Either you remember the formula or you can remember the concept how to find out the equivalent thermal conductivity in case you forgot the formula. So I hope I made it clear. Now let's move forward to the next problem. Again, this problem, it is based on the chapter of moving charges and magnetism. It says that when a charged particle is projected perpendicular to a magnetic field, then. So if a charged particle is projected to a, you know, perpendicular to magnetic field, then what happens? See, the magnetic field F, it is equal to Q times of V cross B. Right? So this magnetic force, it will be perpendicular. It will be perpendicular to the velocity. So this force, this magnetic force, it is perpendicular. It is perpendicular to the velocity of charged particle. So what kind of a trajectory will it have in this case? See, if the force is perpendicular to the velocity, so the work done or the power supplied by this force will be 0. Since the force is perpendicular to the velocity, so you can very well assume that, or you can very well understand that the work done by this magnetic force on this charged particle will be 0, or the power supplied by the, this magnetic force will be 0. So this magnetic force can do no work, right? And since this charged particle is only experiencing the magnetic force, and that force is also not able to do the work, so from the work energy theorem, work done by all the forces is equal to change in kinetic energy. And the only force that is acting is a magnetic force, and that force is doing no work. So change in kinetic energy should be equal to 0. It means that the kinetic energy should remain constant. Now we very well know that half mv square is the formula for the kinetic energy. Now mass is held constant. Mass is obviously constant for a charged particle. What else should be constant if kinetic energy needs to be constant? The speed. So from here I concluded that speed should remain constant. So if you are getting what I'm trying to say, this particle will move in a circular path. So if this is the velocity of the particle, that's how the magnetic force is going to act, Fm. If this is the velocity of the particle, that's how the magnetic force is going to act, right? So V cross B. So magnetic field should be something like this into the plane of the paper. So in this case, the straight trajectory, not straight trajectory, it will undergo the circular path and it will be a uniform circular motion. Why uniform circular motion? Because the speed is going to remain constant. Now, since the speed is going to remain constant, it means that the kinetic energy is also going to remain constant. And what about the velocity? Velocity being a vector quantity, it consists of magnitude as well as the direction. So even if the magnitude is held constant, the direction is continuously changing. It means that velocity cannot remain constant, right? And let's talk about the linear momentum also. Linear momentum, again a vector quantity. The magnitude will remain fixed, but the direction will keep on changing. The direction will keep on changing. It means that the linear momentum will also not remain constant. So the constant part should be the speed and the kinetic energy, and the velocity and the linear momentum, they both should vary. Now let's head to the option. It says that its velocity and kinetic energy are constant. Kinetic energy is constant, but not the velocity. So this one is wrong. Let's go to the second option. It says that its speed and momentum are constant. Speed is constant, but not momentum. So this one is also wrong. Third one says that its speed and kinetic energy are constant. Speed and kinetic energy, yes, this one is right. Fourth one says that its momentum and kinetic energy is constant, not momentum, only the kinetic energy. So this one is also wrong. So the correct answer to this problem should be option 3. Right? And if you understood this problem, I'll give you the problem again from the actual paper of the NEET, and it was asked in NEET 2023. It says that a uniform electric field and a uniform magnetic field. Now in the previous problem that we were discussing, there was only the magnetic field, but this time with the variation, we have introduced the magnetic field as well as the electric field. So you have an electric field and magnetic field. They are acting along the same direction in a certain region. The key point is they both are acting in the same direction. An electron, if an electron is projected along the direction of the field with certain velocity, then, okay, you need to comment about the speed. Okay, someone is commenting the answer as third option. We'll turn towards left. Are you commenting the answer of this problem or the previous problem? If you know the answer to this problem, you can put the answer in the comment box. So if this is the electric field and if this will be the magnetic field, both the fields are in the same direction, right? Now an electron is projected along the direction of field. So an electron, it is projected along the direction of field. Now dear students, we very well know that the magnetic force, it is given by Q V cross B. V is the velocity of the charged particle, B is the magnetic field. Now you need to perform the cross product, but the angle between V and B. Angle between V and B. This is the magnetic field. So let me write a B. So angle between V and B is 0. And if the angle between two vectors is 0, then the cross product is going to be 0. It means that this electron will not experience any magnetic force, right? Okay, this problem option 1. Okay, so this electron is not going to experience any magnetic force. This part we concluded, right? Now what about the electric field? We know that the force due to electric field is Q times of E. But be very careful, you have an electron over here. So if you have a field in this direction, it means that this electron is going to experience electric force in this direction, Fe. Right, Fe will be in this direction, and the velocity of the electron is in this direction. So velocity is in this direction, the force is in this direction. It means that this the velocity or the speed of the particle is going to decrease, right? So the correct answer to this problem should be option 1, that is the speed will decrease. So this one is wrong, this one is also wrong, and this one is also wrong. See, that's how you deal with the actual problems of the NEET examination. Simple problem. You just need to have presence of mind to solve the problem. So the correct answer to this problem should be speed will decrease. I hope you understood the problem. Okay, if you understood the problem, let's move forward to the next problem. And next problem, right in front of you, it is based on the chapter of system of particle and rotational motion, right? It says that two bodies of different masses of 2 kg and 4 kg start moving with velocities 2 meter per second and 1 meter per second towards each other due to mutual gravitational attraction. What is the velocity of center of mass? So you need to find the velocity of center of mass, and the two particles are moving due to mutual gravitational attraction. So you have a particle A like this, you have a particle B like this. It is moving, both are moving towards each other. Let me assume that the velocity is V1 and let me assume that velocity is V2. Right? They are moving towards each other, right? Good afternoon. And the mass is M1, the mass is M2. So if I consider this as my system, then this system is experiencing no external force. These forces due to these mutual forces, they are internal forces to the system. No external force is acting on the system. Now what is the meaning of no external force acting on the system? If external force acting on the system is 0, it means that the center of mass will not move. It will remain in its original position only. Now let's go through the problem. Two bodies, they start moving. What is the meaning of start moving? It means that initially the center of mass was at rest. Initially center of mass was at rest, and even if they move due to the mutual gravitational attraction, this will be internal forces. No external force is acting on the system. No external force is acting on the system. That means that acceleration of center of mass should be equal to 0. That means no change in the velocity of the center of mass, which means that velocity of center of mass initially was 0, so it will remain 0 only. So the correct answer should be option 4, right? And you can use this formula also to find out VCOM. For two particle system, it can be written as M1V1. Let me put the vector M1V1 plus M2V2 upon M1 plus M2, right? You can use this formula also, or you can directly go with the concept. So you have two masses of 2 kg and 4 kg, right? So this is of 2 kg and this is of 4 kg. And this 2 kg one is moving with a velocity of 2 meter per second. And this 4 kg one is moving with a velocity of 1 meter per second. Right? So VCOM you need to find. VCOM. So it should be equal to M1. M1 is 2 into 2 into 2. So 2 into 2 I cap plus M2 is 4 into minus 1 I cap upon 2 plus 2 is 4. So it is equal to 4 I cap minus 4 I cap by 4. Again, VCOM is coming out to be equal to 0. VCOM is coming out to be equal to 0. It means that the center of mass will remain at rest. Either you go with this method, or you can directly use the concept that if net external force acting on the system is 0, the center of mass will remain at rest. And if the center of mass was moving with certain velocity, it will continue to move with that velocity in the case when external force acting on the system is 0. So this is a simple question. So the correct answer to this problem is option 4. You can go the either way, either this way or the other way, right? Now dear students, I hope you understood this, and with this I'll end my session for you, and I'll continue with the next session. In the upcoming session I will be there with you for discussing the problems of other chapters. So till then, please keep tuned, and all the best for your preparation of the NEET examinations. Thank you.